Hello everyone, this is Jeon Jung. Today I will explain Introduction to Computer Networks course. This is Jeon Jung. Today we will study Chapter 3, Transporter Layer Part 2. This is a roadmap for second part of Chapter 3, Connection-Oriented Transport TCP. Consisting of a segment structure, reliable data transfer, flow control, connection management. The TCP specify the internet specifications RFCs 393, 1122, 2018, 5681, 3323. This protocol is a point-to-point, one sender and one receiver, and reliable in order byte stream, no message boundaries like UDP diagram. TCP support the full duplex data, which means bidirectional data flow in the same connection. Also, it supports the concept of maximum segment size MSS. And TCP support a cumulative X for pipelining. So pipelining, it supports two control. One is a TCP congestion control and the other one is a TCP flow control. Those control set a window size for pipelining. TCP is connection oriented, which means it adopts handshaking, exchange of control message to initialize the sender and receiver state before actual data exchange. Also, the flow controlled. Sender will not overwhelm receiver using flow control. This is a TCP segment structure, TCP header and the payload. Okay, so 16-bit source port number and the destination port number, and 32-bit sequence number indicating the start of data stream, and acknowledgement. This one is indicate data received well. So acknowledgement number usually the expected sequence number in next TCP segment. And TCP has also a lot of flags, and also TCP support 16-bit checksum like internet IP checksum to detect the bit error, and also it has options. Okay, and last one is this one is application data payload. Before that, TCP also has length. This length is TCP header length. Also, other flags. A is acknowledge. If this is a set, this TCP segment is acknowledgement, and R means reset. S is a sync, the start of the connection, and the Fine pin is finish, the tear down of the TCP connection. Okay, and this is the receive window. It is used for control, indicate the number of bytes the receiver willing to accept. Okay, and also TCP support explicit congestion notification, C and E flags. Also urgent and the pointer, okay, for urgent data, deliver urgent data. it is called out of band delivery. And now TCP sequence number is a byte stream number of first byte of this segment's data. Okay, so this is the sliding window. So this is similar to the TCP sliding window, similar to go back and selectively repeat window concept. Okay, so the green one is already acknowledged, and the yellow one means sent but not acknowledged yet, implant segment. And the blue one case we can transmit usable but not yet sent because application layer didn't send the data payload to TCP layer, and gray is not usable. Okay, and the acknowledgement is the sequence number of the next byte expected from the other side. Also, it supports a cumulative ACK. Okay, so this is a TCP acknowledgement. Okay, number and the flag. Okay, this one is a TCP segment number. So the question is how receiver handles out of other segment. TCP specification doesn't say up to implementer. Okay. Let's take a look the simple telnet scenario. Telnet is used to remote login service. So nowadays we are using secure cell SSH. In the past we used the telnet. So you type in your keyboard C, and then so initially we randomly select the sequence number, so such as 42, and acknowledge means we assuming the TCP connection between host and a host B established. Okay, so current sequence number 42 just sends one character C to host B, and at that time acknowledgement 79 indicate B sequence number is 79. Okay, and then host A's sequence number 42, acknowledge is 43. So sequence number and then data size. Okay, so this is the first data, right? And then next one is 43. This is the acknowledgement, and then host A X receipt of echoed C. Okay, so type C and then echoed C and then acknowledge. Okay, so acknowledgement will be used by host A as a sequence number, and then X is you can see the next number sequence. Okay, is 80. That's why acknowledgement 80. Okay, and the TCP laundry time RTT, and then time how can calculate. The question is how to set TCP timeout value. So longer than round trip time, but round trip time varies. Okay, so which means round trip time are kind of up and down. Okay, over time. So too short round trip time, so premature. So timeout we make some too short case premature timeout occurs, which means unnecessary retransmissions are caused by this premature timeout. Too long case slow reaction to TCP segment loss. Okay. The next question is how to estimate round trip time. So once we calculate the round trip time, and then we can calculate the timeout based on round trip time. We have a concept of sample RTT. This is a measured time from segment transmission until acknowledgement receipt. Okay, so we ignore retransmissions for calculation of this sample RTT. Sample RTT will vary. Want to estimate RTT smoother. Average several recent measurements, not just the current. So we are using some exponential weighted moving average. Okay, so the formula is like this. Okay, so we want to calculate estimated RTT. So estimated RTT is a historical value, and this is a sample current TCP segment measure round trip one round trip time. Okay, and then the percent is alpha is just 0.125, means 12.5%. Weight is current sample RTT. Remain the portion is 1 minus alpha, means 0.875, 87.5% based on the past historical value. Okay, so we put the higher value, historic value, and we explore the current round trip time using sample. So this is called the moving average. Exactly, we can say exponential weighted moving average. So this figure shows each sample RTT is very fluctuated like this. However, estimated RTT is moving average is smoother than sample RTT. So timeout interval, estimated RTT plus safety margin used. So large variation in estimated RTT want a larger safety margin. So we can calculate right now timeout value here. Timeout the interval for TCP segment. Estimated RTT we calculated previously like this. Exponential weighted moving average. And then we 4 times the variation of RTT. So this is safety margin. This is estimated RTT. And then derivation of RTT, this is exponential weighted moving average over sample RTT derivation from estimated RTT. So derivation RTT is also similarly past derivation of RTT 1 minus beta. So beta value is currently 0.25, okay, 25%. This is 75% historical value of derivation of RTT, and this is a current sample RTT based difference. Sample RTT, and this is estimated RTT historical value. We calculated previously, right, according to previous calculation. And then this is the difference from historical value, and this one is the current sample value. Okay, and then times 25%. This is current deviation, and then this is 1 minus beta. This is a first deviation value, and then we also calculate like moving average. Okay, like estimated RTT. So based on this calculation, dev RTT 4 times plus estimated RTT, eventually TCP segment timeout value. Okay, next move on TCP sender. So event data received from application. So the TCP sender. So we also will see TCP receiver. Okay. So application layer gives the data. It is called event, and then create TCP segment with the segment sequence number. And sequence number is the byte stream number of the first data byte in our segment. And then we start the timer. Okay, so TCP case we can make the timer. Okay, for segment. If not already running, think of the timer as for oldest unacknowledged segment. Okay, and then this oldest unacknowledged segment expire, and then we can transmit that segment. Okay, So TCP timeout value is we calculated previously, and then timeout happen, we transmit the segment that caused the timeout, and then restart timer. And the event. The secondly, previously we data received from application layer. First event. Second is a timeout. Third event is acknowledgement segment received. Okay. So if ACK acknowledges previously unacknowledged segment, update what is known to be acknowledged in the previously sliding window, and then start timer if there are still unacknowledged segments. Okay. So we can see now TCP receiver. Previously we saw a TCP sender. So okay, event at receiver. Okay, so receiver point of view, a library of in order segment with expected sequence number. This is regular state condition. Okay, and then all data up to expected sequence number already acknowledged. And then TCP receiver action. This is event. The action is we performing delayed act rather than immediately respond act. Wait up to 500 milliseconds for next segment because we try to spot the cumulative acknowledgement. Also, we reduce the number of acknowledgement segment. If no next segment, send ACK. Okay, and then the second event is arrival of in order segment with expected sequence number. Okay, but one other segment has ACK pending. So in that case, immediately send single cumulative ACK acknowledging both in order segment. Okay, so the event is a library, in this case out of order segment higher than expected number, which means some in the middle some segment are lost, which means gap detected. So in that case, immediately send the duplicate ACK. Eventually 3 duplicate ACK makes a sender retransmit that corresponding segment. Okay, that is past retransmit. We'll learn later. And a library of a segment that partially or completely fills gap. In this case, also immediately send ACK, provided that a segment start at lower end of gap. Okay. So we checked like this. Okay. So blue one is the keywords for event and action of a TCP receiver. Okay, TCP retransmission scenario. Okay, so the acknowledge lost. Okay, so the timeout happened, and then corresponding TCP segment sequence number 92 retransmitted. Okay, and acknowledged well. And here two segment. Okay, sequentially transmitted. Okay, but here premature timeout happen here, and so this second segment, this acknowledge generate second, okay, usually, but here we transmit here. So and the timeout happen, and then what happened? Okay, so transmit this segment, the first segment retransmitted. Okay, and then this guy already received, right? So in that case, so 90 100, right? And then this guy is received, right? So next one is this second act, right? So this act is generated, but previously to this and this is the same act, right? So kind of a duplicate act. Okay. but there is no problem. Okay, so we received well. We can ignore this second acknowledgement. And cumulative egg covers for all the lost acknowledge. Okay, so this one lost, but this egg is cover previous one. Okay, and then the next segment can be generated. And that from now on we'll study TCP faster retransmit. So here so 1 2 3 4 5 segments are transmitted, and second data segment lost. Okay, and then this guy is generate acknowledge 100. This is, but other case also generate duplicate egg, because okay, this one is lost, right? So this segment requested by the host B, right? So, and then this first acknowledge, and then next three consecutive data segment are liable to generate three duplicate egg. Eventually, first one and then three duplicate egg. Eventually, four total acknowledge means this segment are lost, and then host A retransmit this one rather than waiting for timeout for this segment. Okay, timeout. So this is a fast retransmit. Okay, so receipt of three duplicate eggs indicates three segments received after a missing segment. Lost segment is likely, so retransmit. Thus, this is a fast retransmit. Okay, so TCP fast retransmit if the sender receives three additional eggs for the same egg, the same data, triple duplicate egg. Eventually, the original egg and the three duplicate egg total 4x, the same data, resend on acknowledged segment. Okay, so don't wait for timeout. Okay, so next one is connection-oriented TCP, the flow control and connection management we'll study. Okay, so the flow control case receiver perspective, so receiver protocol stack. Okay, so here IP layer TCP and socket layer. Okay, especially TCP socket has some the receiver buffer. Okay, so network layer received some datagram and then forward to this. Okay, TCP socket layer. Okay, and then TCP socket layer got data and then push up to application layer, application process. Okay, the question is what happens if network layer delivers data faster than application layer removes data from socket buffer. So in that case the socket will be queue up, and this is overflow, and the packet will be data will be overthrown, and we need to control the transmission speed of a sender, right? So that's why TCP flow control is required. Okay, like the too fast sender. Okay, so receiver they're kind of throttled. Okay, so this is the TCP segment header. So receiver window is called the receiver window size. RWND is the receiver window size. Okay, so flow control, receiver controls the sender, which means the receiver controls sender's speed in order that sender won't overflow receiver's buffer by transmitting too much too fast. Okay, so RWND, this is receiver window side. Okay, so TCP case, TCP the indicates in the header receive per window size, okay, field, alt-branded field, and then advertise free buffer space. So this figure shows the whole buffer size is receiver buffer, this one, and the alt-branded is free, available for next TCP segment. This is already buffered data, okay. So it guarantees the receiver buffer will not overflow, okay. So receive a buffer size usually 4K bytes, okay. And then this is receive a window size alt-branded, okay. Okay, next topic is TCP connection management, like three-way handshaking and also teardown connection. So the TCP connection is established, okay. So this is client, this is a server, right? So it has some state information because the TCP case using a state transition diagram, okay. So connection state is currently established, okay, and the connection variable case sequence number, receiver buffer size, and so on. So client make a socket. This is a Java code. So the host name, DNS name, and the port number, and then make this socket, and then this guy is, and then it calls the connect, okay, function. So eventually accept socket return, okay, for the client, okay, IP and the port number, okay. So the agreeing establish, okay, we can do TCP establishment using two-way handshake, but two-way handshake has some problem, okay. So that's why three-way handshaking is used for TCP. So Alice and Bob communication scenario, let's talk, okay. So establish, okay, message exchanged. So request some sequence number and accept, okay, connection, okay. So will two-way handshake always work in network? Okay, usually, yeah, work. Okay, variable delay, retransmit the message reordering, cannot see other sides, okay. The major problem is some packet loss happen or delayed of some acknowledgement, some problem happen, okay. So two-way handshake scenario case, okay, choose random sequence number and then request message, establish the accept, kind of acknowledge, okay, and then the data transmitted, okay, 1 plus 1, x plus 1, and transmitted, accepted, acknowledged. This one, connection completed. There is no problem, okay, no problem. So problem case, okay, here choose x and then establish here, and then connection terminated, okay, and then server forgets x. But retransmit request, okay, x, okay, because of some timeout happen, and actually after that, and then acknowledgement here, right? So in that case, this one is okay, receive the server again, server forgot the x, and then new connection using previous x, okay, and then acknowledge, okay. So half open here, this server open, client is closed, right? So this is a problem. The second problem is here. So okay, established, data accepted, okay, and then retransmit open, this one is also established here, and then also the data also retransmitted because of a timeout happen, and then so even though previously client and server terminated the session, but this one is established connection and the data received, okay. So this one, all the data received twice, this is also problem, okay. problem duplicate data accepted. Okay. From now on, I will explain TCP three-way handshaking. Left hand side is client, right hand side is a server. Okay, so client made TCP socket and then connect to server. Okay, so server name and server port number. So name will be translated into IP address of a server, and TCP sync bit in header and the SQL number X, and the server state. Socket created the bind each port number and listen, waiting the queue size 1, and this accept. Okay, waiting for client connection request, and then it receives the connection request sync message, and then choose a random SQL number Y, and so acknowledgement is X plus 1 because this length is is 1, and then received and then generate sequence number. Actually sequence number here don't it is not described. We just focus on acknowledge here, so just acknowledge case sequence number Y is received and then Y plus 1 generated. So and then the client state is a listen state connection call. After that sync sent, and then receive the sync and the ACK message from the server and then established. This is client state transition, and server case listen and then sync received and then transmit sync and ACK, right? So and then received acknowledged, and then server state is established. Okay, so we have analogy human three-way handshaking protocol. So kind of climbing. Climbing here. So this is a climber, and then this guy is assist, right? So this guy saying on belay means you put some clip and then you have this kind of the belaying devices. So this is braking, this is a kind of this one is right, so a tubular style device assist your this is humans. So on delay, and then this guy and then saying belay on, so you can climb, something like that, and then this guy I'm climbing. So ask a question, kind of sync message, this is a kind of sync ACK, and then climbing, this is ACK. So this is a human three-way handshaking protocol. So in order to watch how to belay in YouTube, you can click this link. Closing. So previously we saw TCP establishment. Now TCP connection closing. So client over server each close their side of connection. So TCP header, it has the pin bit. Finish bit. Respond to receive the pin with acknowledge. On receiving pin and acknowledge can be combined with its own pin. So simultaneous pin exchange can be handled. Appendix this slide, you can see this the closing TCP connection. Let's move on. Principles of congestion control. So we'll see the theory of congestion control. The principle, you can see this is road network. A lot of vehicles, truck, cars, right, mess up. So somehow this is a kind of a network, internet. You can imagine. So car is a packet. So too many standard sending too fast. Somehow we need to okay, release this network internet. So in how to that, sender speed should be slowed down. Informally, too many sources are sending too much data too fast for network to handle. Manifestations, the long delay, queuing in louder buffers. Okay, we have analogy, packet loss, buffer overflow at and louder. So this is different from flow control. Flow control is the receiver Windows side is notified using acknowledgement. Okay, message, right? Kind of. Um, so this is a different flow control, conject control. This is receiver, the available buffer space, and sender control transmission speed. Congestion control is a network-wide consideration. So some packet loss happen because of some duplicate act or three duplicate act or timer out, right? Timeout case network is some serious problem. So we have scenarios. The first scenario is causes cost and congestion. Okay, simple. Okay, so list the scenario. We have a host A, host B, and two server. In the middle we have one router, like this. Okay, so also we assume infinite some buffer. Okay, so original transmission okay, data generation arrival rate is lambda in and receiver rate is lambda out throughput. Okay, and the host B also similarly. Okay, transmit like this. Okay, and then this link and output input capacity is R. Okay, mega bps for example. So to flow here. Also we are assuming no retransmission needed because infinite buffers. Okay, so what happens as arrival rate lambda in approaches a half of R over 2. So we have this graph. Okay, so the input and output is proportional until input is R over 2, R over 2, right? Because they share this maximum bandwidth R okay, fairly. In that case, over this and output should be okay same or half over R. And the delay case, the input delay is this, the infinite. Remember this queuing. So a lot of packets line up close to R over 2 each. Okay, the path, right? So delay will be close to very big number. Okay, eventually it is close to R over 2, the almost the infinite number approaches the capacity. Okay, let's move on the scenario 2. Okay, the scenario 2 case. Okay, difference is the finite buffer here. So finite buffer means some packet, you know, the dropping happen here, packet loss happen, and we have okay, two input, application layer, okay, input and output here. But because of this finite buffer, packet dropped and then retransmission required. In that case, transport layer input, this one is greater than because the retransmission packet is occurred, right? So original data, but some original data plus return data can be delivered. Okay, so that's why the rate is greater than original or equal to. Output is the same. So one assumption, idealization, perfect knowledge, which means the sender sends only when louder buffers available, like this. Okay, available and then deliver, prevent some dropping because available buffer. If this is occupied, other okay, packet, the new packet will be dropped. Okay, so that's why this assumption. So in that case, a library, okay, this input rate the lambda in, and then output throughput is lambda out case proportional until R over 2, because the two paths connections share the link. Okay, so packet can be lost, dropped at louder due to buffer, okay, the fullness, okay, because of this finite buffer. And sender knows when packet has been dropped, only resend if packet known to be lost. Okay, so packet is delivered like this. Okay, copy is prepared. Okay, so but here dropped. Okay, and then new copy is delivered. Okay, and then delivered. So that's why, so lambda in prime, this is greater than or equal to lambda in. And then here, so actual, good put, we can say good put in terms of application layer throughput, right? So this, before that, transmission case, transport layer point of view also overhead here, right? So this is okay. And then initially same, but here some discrepancy happen here. So because when standing at R over 2, some packets are needed retransmissions because of this finite buffer full overflow and the wasted capacity due to retransmitted. Okay, so this kind of retransmission transport layer. Okay, however, realistic scenario, unneeded duplicates. Okay, so unneeded duplicates packet happen. So packet can be lost, dropped at the louder to for buffer we saw, right? So require retransmission. Also, the sender times can time out prematurely. That's why sender can transmit two copies, both of which are delivered duplicate. Okay, this is unneeded duplicate. Okay, so one copy delivered here. Okay, so let's see. Okay, okay, first one is delivered. Like this, and then premature, okay, timer happened transmitted, so two copy delivered, so it is called unnecessary duplicate transmission. Okay, so in that case here more the worse than the previous one. Okay, okay, so this figure shows the relations between input rate lambda in prime and the output rate lambda out. Okay, throughput. So when sending at the R over 2, some packets are retransmitted because of timeout prematurely, including needed and unneeded duplicates that are delivered. That's why here actual throughput is lower. Okay, so wasted capacity to unneeded retransmitted. Okay, so the first part is a kind of retransmitted, and this one is unneeded packet. Okay, so the cost of conjunction, more work retransmission per receiver throughput. Also, the worst one is unneeded retransmissions. Link carries multiple copies of a packet, decrease maximum achievable throughput. Okay. Okay. Next, the scenario 3. Okay. Previous scenario 2. Now scenario 3. So here, for host A, B, C, D, they make the connections, okay? So like this, a kind of a mesh network, okay? Kind of the A connected here, C, and then C connected the A, okay? Not full mesh, but a kind of connected this one, okay? So for sender, multi-hop passes and timeout retransmission happen, okay? And here we have routers, 4 routers with finite shared uplink buffers, okay? Okay, similarly. The question is what happens as lambda in and lambda in prime increase, okay? The answer is as red, okay, red this one, okay? The red lambda in prime increases, or alive in blue here, the other connection here shared by red, okay? So blue packets at the upper queue are dropped because of the red packet occupies this link. The blue throughput goes to 0, okay? That's why this kind of thing happen, and the input rate lambda is more than this kind of okay output, and then this kind of dropping happen, okay? So this is because of the the four nodes are occupying, and they compete with each other for usage of their uh, transmissions, okay? So another cost of congestion, this problem, okay, happen when packet dropped, any upstream transmission capacity and buffer used for that packet, like the red one, okay, this one, and then the wasted, okay, because the other one is wasted. So the insight based on previous our observation, the throughput can never exceed the capacity, right? So initially, okay, the proportional linear increase, but once reaches R over 2, and then output is just the same. And the delay is input rate is lambda in close to a half of R, which means R over 2, delay going to infinite. And the loss retransmission decreases effective throughput, right? So transport layer retransmission required, okay, and then actual the throughput reduced, and then unneeded duplicate also further decreases effective throughput. And then upstream transmission capacity buffer is wasted for packet lost, okay, downstream because of other stream competition. Upstream transmission is wasted, and then like this, okay, competition of two connections. And the approaches toward the congestion and control, so end-to-end congestion control. So TCP case no explicit feedback network originally. Congestion inferred from observed loss or delay because of timeout happens. Approach taken by TCP original version. So the data transmitted acknowledged here, okay? And next one is network assisted congestion control. Router provide direct feedback to sending receiving host with flows passing through congestion router, like this one. May indicate congestion level or explicit set sending rate. This one can mark, okay? So it is called the TCP ECN ATM asynchronous transmission mode, transport mode, okay? This is kind of some advanced cell switching. and DC-bit protocols are proposed in the past. Okay, so router embed explicit conjunction info. Okay, next one is TCP conjunction control. So TCP conjunction control is called the AIMD applicative. Okay, so this one is additive increase and multiplicative decrease. So approach is that senders can increase the sending rate until packet loss, that is conjunction, occurs, then decreases the sending rate on loss event. So we have a two-part increase is like this additive increase, but dropping case multiplicative, because a half divided by 2, right? So multiplicative decrease. So AIMD. So increase sending rate by one maximum segment size every RTT for conjunction window size CWND until loss detected. And on the other hand, decrease multiplicative decrease case cut transmission rate a half, okay, in half at each loss event. So this shape is a saw tooth, okay. This is a tooth tool to cut the wood, okay. The probing for bandwidth. So TCP AIMD multiplicative decrease detail sending rate is cut in half on loss detected by triple duplicate act. Okay, TCP linear version using this one. Okay, and cut to one maximum segment size when loss detected by timeout. This is a TCP Tae Oh. So TCP Tae Oh case duplicate act over and timeout happen always CWND goes to one maximum segment size, but TCP linear case just duplicate act case, triple duplicate act case is just CWND is cut by a half, but it fast recover, which means increases, okay, the linearly, okay, not CWND set to 1, okay. But the timeout happen in linear case. Similarly, CWND connection window size set to 1 maximum segment size. So why AIMD? AIMD, a distributed asynchronous algorithm, has been shown to optimize congestion flow rate net-wide, okay, and have a desirable stability properties. That's why AIMD is popularly used. The TCP congestion control, this is TCP sliding, okay, window, and the green one is last byte. This one is already acknowledged. The right hand side, this is last byte acknowledged, and yellow one. And this one is conjunction window size. We can transmit this one. The yellow means implied packet sent but not yet acknowledged. This one is available for the future application data payload. Okay, so this is last byte sent, available but not used. This gray one is not available yet. So TCP sender limit transmission, last byte sent. Last byte sent, this one, and last byte acknowledged. This last byte acknowledged. Okay, so this one. Okay, this amount is less than or equal to CWND. Okay, this right hand side yellow can be this rightmost. Okay, so CWND is dynamically adjusted in response to observed network congestion, implementing TCP congestion control for net-wide. So TCP sending behavior. So remember, CWND case, there is no field for CWND in TCP header. This is internal state variable, system variable. So locally send CWND bytes, okay? So don't confuse by RWND, receiver buffer side. Okay, that case, the TCP header has field. So CWND byte send and wait the RTT for acknowledge, then send more bytes. Okay, so which means during round trip time, transmit the first segment. Okay, and during the segment or consecutively send the segment, and then all data is received. Okay, acknowledged by this one means round trip time. Okay, and then it can transmit increases by 1 CWND plus 1 maximum segment size. Okay, so this is congestion avoidance. So we have two parts TCP congestion control. First one is TCP slow start, the second one is congestion avoidance. Okay, so the slow start case, initially CWND is one maximum segment size, just one segment TCP. Round trip time here, just one segment. And then if one segment acknowledged here, two segment deliver. Okay, and then one round trip time, and then 4 segment. After one round time, 8, which means exponentially increases 1, 2, 4, 8, right? So increases CWND for every acknowledge received, right? So every acknowledge received and then transmit 1, something like that, eventually increases CWND exponentially. But if we receive the transmit 1 just and then 2, and then 2 acknowledge received and then send 3, and 4 received and then 5. This approach is congestion avoidance. The summary: initial rate is slow but ramping up, speed up exponentially fast. Okay, so that's why we need another part, the congestion avoidance after slow start. The question is, we have another system variable, slow start threshold, SSTHRES, slow start threshold. This variable is criteria or border. So slow start from one segment and up to here exponential increases and then reaches this, and then congestion avoidance phase, which means CWND segments all transmitted, and then that amount of segments acknowledged, and then CWND increases by 1 maximum segment size. Okay, so the question is, when should the exponential increase switch to linear? Exponential increases and then linear. So slow start threshold is used. And the question is, CWND gets to 1 over of its value before timeout. Okay, so CWND gets 1 over 2 before timeout. Okay, so this pair usually CWND 1/2 is slow start threshold. So we have a slow start threshold. Loss happen as slow start always half of CWND. Okay, just before loss happen. So it increases and then slow start stops, and then this congestion avoidance, and then transmission round. Okay, so first round, second round, third. So CWND all segments and then received here, but this is some problem happen. So 3 duplicate act over timeout event happen. So 3 duplicate act, we assuming TCP Linux case just okay, slash start value set to this ctRND size, which means 6, and then start path recovery, which means increases ctRND linearly. This is TCP Linux. On the other hand, the TCP Tae Oh case, whenever 3 duplicate act or timeout happens, always the ctRND set to, okay, here, okay, 1. But this one case, okay, so cwnd is just a half of previous one, and the slow start is adjusted, okay, here. And then TCP Tae Oh case, the slow start exponentially increases cwnd, and then the conjunction avoidance phase, okay, starts. Okay, so check out the online interactive exercise for more example. Okay, this link you can click. Okay, and the summary. So we have a transition diagram, slow start, conjunction avoidance, and the path recovery. Okay, so we have event and the action. So this diagram shows this kind of happen. Okay, slow start. Okay, slow start, and then cwnd greater equal to slow start is transit conjunction avoidance. Okay, so do at the acknowledge. Okay, and this is important. And the cwnd is maximum segment times maximum segment size over cnd. Okay, this meaning is, so this amount of ctRND segment, okay, transmitted or acknowledged according to ctRND segment. So this accumulated one is ctRND, right? This is divided by the same ctRND MSS multiplied some time, we can say n divided ctRND is equal to 1 case. Eventually m size ctRND plus MSS is increased. This means the linear increase. Okay, this avoidance duplicate case count, and then duplicate is 3 case. This is going to path recovery. So in that case, slow start threshold set to ctRND divided by 2, and the ctRND is slow start this value, and then plus the 3 segment, and then retransmit the missing segment. Okay, and then this move to there, and then so this is path recovery duplicate act. Okay, so ctRND, and then ctRND maximum segment. Okay, so increases, okay, linear. Okay, and then so this timeout happen, and then this going to Tae Oh or Linux, regardless of that, set to threshold value is set to ctRND divided by 2, and the ctRND is set to 1, and duplicate act count is 0. Okay, and then so start again. So timeout here, you acknowledge. Okay, so now we have another approach, TCP cubic, TCP AI, okay, MD, right? So is there a better way than AIMD to prove that prove for usable bandwidth in the pipeline in the past? So this is okay, AIMD pattern, right? Sawtooth pattern. Okay, the cube case, we have this is max AIMD. I have a max here. So the W max is a sending rate at which conjunction loss was detected. So congestion loss means the 3 duplicate act. So congestion state of a bottleneck link. The bottleneck is important, right? So we have a pipeline. So a certain part of pipeline is very wide, and then certain is very the okay narrow. This is bottleneck, and then wide again. Okay, narrow, wide. Okay, so end to end in TCP end to end connection. In the middle, we have a bottleneck link, a low bandwidth link. So congestion uh, hasn't changed much. Okay, during the interaction. So after cutting a length divided by window in half on loss, okay, and initially lamp to this fast max, okay, faster, but then approach is slow. So we have another approach like this, the cubic approach. So from here, more quickly, right? More quickly increases, but approaches this y max, w max, and then slowly past. Okay, eventually the same AMD max value. So this is a cubic. Okay, so it is a kind of a cubic curve and drop the cubic curve or something like that. Okay, this is the better approach. Okay, so k is a time point, right? This is a time point. Okay, k. This we can say this time point increases this, and this time k, and then close to here, w max. Okay, so point in time when TCP window size will reach the w max, k is self-tunable. Okay, and the increase w as a function over the cube of the distance between the current time and the k. So if the w is larger, increases when further away k. So and the smaller increases cautiously when near k. Okay, like this. Okay, so it is k value. It is k value, and then the power rate is okay large increases, but closed okay small increases, and then dropped, and then large increases, small increases. Okay, so this blue okay dashed line is TCP cube behavior. TCP Linux case like this. Okay, so TCP cube default in Linux, most popular TCP version, and for popular web servers. Okay, let's move on. And TCP and the conjunction bottleneck link here. So TCP classic or cubic, AIMD and cubic, increases the TCP sending rate until packet loss occurs at some router's output, the bottleneck, for example here. Okay, so the packet queue bottleneck, this case router almost never empty because of bottleneck link. Many flow share this link. Sometimes overflows packet loss happen. Okay, so from source to destination and the round trip time here. Okay, understanding conjunction, useful to focus on conjecture bottleneck link. Okay, so we have a better some conjunction scheme. Consider this RTT. And insight, increasing TCP sending rate. Okay, here sending rate will not increase end-to-end throughput because of here a lot of queuing delays. Okay, and then also the packet drop happen here. So this increased rate will not increase end-to-end throughput with connection bottleneck. Okay, So increasing TCP sending rate will increase the measured RTT because of the more delay, waiting, queuing time. So keep the end-to-end pipe from source to destination pipe just full, not but fuller. Okay. So that's why we come up with the new congestion control. It is called the delay-based TCP congestion control. So keeping sender to receiver pipe, okay, from sender to receiver this pipe pass just full enough, not okay, but no fuller. Keep a parallel link busy transmitting, but avoid the high delays bubbling. Okay. So delay based approaches case. We can define the RTT min case minimum of the RTT in the case of uncongested paths. Okay, so uncongested throughput with congestion with the CWND here. So this is CWND divided by RTT. Okay, this is the throughput we defined similarly previously. Okay, so measure the throughput, the number of bytes sent in the interval of last RTT interval and divided by RTT measured. Okay, so during this RTT, this amount of bytes delivered. So this is a measure the throughput. So we have two condition and action. The measure the throughput here, throughput is close to uncongested. Okay, so this is uncongested window case. Case still it is good, right? So not congested means, right? So path not congested. In that case, we can increase CWND linearly. Okay, increases okay transmission speed. Eventually, throughput will be good. Okay, receiver side. On the other hand, the measure the throughput far below means congested network. Okay, so has congested. In that case, we need to decrease its CWND linearly. So delay-based TCP congestion control, congestion control without inducing or forcing loss. Okay, so it doesn't cause duplicate acts. Okay, so maximizing throughput, keeping the just pipe full, not fuller than okay the capacity, and while keeping delay low, but not fuller. So a number of deployed TCPs take a delay based approach. So Google they made the BBR congestion control. Okay, so they deployed this BBR, one of delay based approach for TCP congestion control, their backbone network. So BBR congestion control. So BBR stands for bottleneck bandwidth and round trip propagation time. So BBR seeks a high throughput with a small queue by probing bandwidth and the round trip time. And the ground up redesign of congestion control, it is not loss based. Loss based means traditional the congestion control. Okay, 3 duplicate act or timeout. Delay based. So this is delay based ECN, explicit congestion notification based, and AIMD. Okay, AIMD based. Additive increase and multiplicative decrease. So click this link. You can see introduction to BBR congestion control from Google. So let's move on. Explicit congestion notification ECN. So TCP deployments often implement the network associated congestion control. Okay, so 2 bits in IP header like TOS field. This is a traffic type. Okay, for QoS, quality of service, okay, marked by network router to indicate congestion. So it is called the policy control to determine marking chosen by network operator. So each and IP diagram delivered, okay, and then in the router, okay, set value here indicate the congestion in the router, okay, and then receive this one, and then TCP side also acknowledge using ECE bit here, and then indicate in the middle it has some congestion, and then this guy is consider this congestion control transmission rate, okay. So destination EC bit on acknowledge segment to notify sender of a congestion, okay, and then involve both IP here, okay, here, and also the TCP, okay. So IP ECM bit marking and TCP header CE bit marking, okay. So okay, TOS stands for type of service, quality of service field, okay, you can remember. So let's move on. TCP fairness. The fairness goal is if K, TCP connection here, two connections, K is 2, share the same bottleneck link over bandwidth R here, bottleneck link is R. Each should have average rate over equally R over K. So here RK is R over 2 connections share or half of R. So the question is TCP fair? Example 2 competing TCP connection here, connection 1 throughput, connection here. So here is connection 1, okay, 1 the throughput. So linearly increases, okay, according to congestion avoidance, adaptive increase, but loss typically happen, and then this, okay, throughput CWND, and the throughput is linearly, okay. So this value is a half decreases, okay, and then linear increases, and the congestion avoidance adaptive increases, and the loss happen, and then this window CWND set to a half of CWND, which means decrease window by factor 2, okay, and then increases and egg, and then this kind. Eventually connection 1 throughput is close to this line, okay. This line is R over 2, so connection 1, connection 2 throughput is equal, okay. This is equal line. Is the TCP fair? Answer: yes, under idealized assumption, the same RTT then picks the number of a session only in congestion avoidance, okay. So fairness: must all net applications be fair? We consider the fairness and the UDP. So multimedia application often do not use TCP because do not want the rate throttled by congestion control. Congestion control case, TCP consider network-wide congestion, and then application transmission bandwidth throughput is sacrificed, okay. Instead of use UDP, UDP case or the video are transmitted at constant rate, tolerate packet loss because they are consider redundancy, okay. Spatial or temporal, okay, redundancy is used, and there is no internet policy use of congestion control. Okay, so PAN is parallel TCP connection case. Application can open multiple parallel connection like multiple HTTP connection over multiple TCP connections. Okay, so between two host multiple parallel connections. The web browser do this. Okay, so in that case, assuming a link of late R, bandwidth is R, and then with 9 existing connection. So the two cases. One case is okay, new application ask for one TCP connection, and then existing one and this one, so R divided 10 equally. But application opens 11 TCP connections, existing 9 and 11, sum is 20. Okay, so in that case, existing one and this one is right, so almost half of the bandwidth is this guy. So which means host uh, web browser open more HTTP connections, other guys can be sacrificed. Okay, this is some problem. So that's why we come up with the evolution of a transporter layer like quick HTTP3 over quick. Okay, so evolving transporter layer functionality, TCP and UDP principal transport protocol for 40 years old. Different flavors of TCP developed for specific scenarios. So the scenario long path 5 large data transfers okay happen. The challenges many packets implied, also loss shuts down the pipeline. Okay, load is a critical one. And the wireless network case, the loss is caused by or due to noisy wireless link rather than the congestion in the network or mobility handover. So TCP treat this as congestion loss. In that case, we need to retransmit. This is a access network side, access base station over router, access point transmit again more frequently. So this is not good, right? So because the current TCP didn't consider wireless network. And long delay link like a cellular link, extremely long RTTs, and the data center network case latency sensitive for some the multiple virtualization and many services are in real time solved. And background traffic flows, low priority background TCP flow. Okay. So moving transporter layer functions to application, which means on top of UDP, we come up with HTTP3 over quick. So and the quick is new transport layer protocol. It is called a UDP based multiplexed and secure transport RFC 9000 specified this standard. You can click and you can get RFC 9000. Quick is an application layer protocol on top of UDP, increase performance of HTTP hypertext text transfer protocol for web data. This one is deployed on many Google servers applications like Chrome, mobile, YouTube apps. Okay, and then recently this was standardized as a general transport layer protocol by IETF. IETF stands for Internet Engineering Task Force. So this is HTTP version 2 over TCP, IP, TCP, TLS, transport layer security. Okay, and HTTP version 2. This is called HTTPS. Okay, and then quick case, instead of TCP, UDP is used, and then over UDP quick. Quick also include the TLS part. Okay, secure transport functionality included. Over that, it support HTTP version 2. So it is called HTTP 3. Okay, so HTTP 3 over QUIC over UDP. Okay, so QUIC adopts approaches we've studied in this chapter for connection establishment, error control, and congestion control. So like TCP features are adopted by QUIC, even though QUIC working on top of UDP. Okay, so error and the congestion control, readers familiar with the TCP loss detection and congestion control will find the algorithm here that parallel well-known TCP. Okay, quick specification, you can refer to this RPC. Previously I put the link for RPC 6000. Connection establishment. Original UDP it doesn't support connection establishment, but QUIC support connection establishment. As a result, reliability, congestion control, authentication, encryption, and state establishment can be done. Especially this connection setup can be done one RTT round trip time. And multiple application level streams defined, multiplexed one single QUIC connection. So one QUIC connection, multiple streams are delivered. Okay, and separate the reliable data transfer, security, common congestion control. This is a good feature. So QUIC connection establishments. Original TCP case, TCP handshake, one round trip time, and then stranded shake, right? And then also the TLS can be done, right? So TLS shaking here, 2 round trip times required. Okay. So however, QUIC case, you can see 1 round trip time is good enough for reliability, congestion control, authentication, crypto state. Okay, so it's good, right? And also QUIC case streams are defined for parallelism. So using streams concept, no head of line blocking happens. Okay, so HTTP version 1.1 case here like this. Okay, so let's compare. Okay, so the thing is multiple connection here. Okay, and then it makes a kind of links, and then so the original HTTP 1 case, this one is shared by, okay, the one HTTP get some big data case, other is a sorted. Okay, it is a head of line blocking, but QUIC case they make this one. Okay, so the congestion control and here encryption. Okay, so they are kind of parallelly used, and then they can equally provide bandwidth, and then there is no head of blocking. Okay. Okay, in summary, chapter 3, principles behind transport layer services, multiplexing, demultiplexing are explained, and the live data transfer and flow control, congestion control, especially TCP, are explained. Instantiation, implementation in the internet, UDP, TCP are popularly used, but nowadays QUIC is popularly used by Google. Okay. Up to next, leaving the network edge application transport layer into the network core. 2 network layer chapters, data plane, and the control plane will be studied. Also, we have additional chapter 3 slides. Go back and sender extended binary state machine here. So sender Okay, you guys can report to this one, and then go back again. The receiver extended file state machine. Okay, you can report to that. The acknowledge only always send ACK for collected received packet within highest in order packet. Okay, and out of packet discard. Okay, so no receiver buffering. This is go back again. Okay, so this is the go back again extended receiver file state machine. TCP sender case, we have also stated transition diagram here according to previous RDT. Okay, so data received application layer create a segment. We randomly select sequence number and then send segment IP layer. Next segment number. Okay, this data size. Okay, and the timer. The currently not running and then start. Okay, so you can follow this event and actions. Okay, so and then TCP survey handle second final state machine. Okay, so this is closed and listen, and then thing received established. This is thing sent. This one. Okay, okay, this one is receiver side. This is server side. Okay, this is client side. So this is the sender, this is the receiver. So closing the tear down the TCP connection. So this client and the server. So the finish message. Okay, so client socket close function called can no longer send but can receive data here. This state. Okay, finish state wait 1 and pin bit TCP flag in header. This bit set to 1 and this sequence number here, and the server is from established the state to close wait and the ACK. Okay, acknowledge number is X plus 1 based on the previous sequence number. Okay, and then this guy's client state is pin wait 2 wait for server. Okay, so the time to wait, the gracious time to receive some data implied from server. Okay, and then this guy send the pin message here and then the ACK here. So this guy can be done parallel. Okay, so the time wait and the cost actually timed for to max the segment lifetime. Okay, so this gracious TCP gracious time cross time. Okay, and TCP through out throughput. So average TCP throughput as function of window size. Okay, RTT. So ignore slow start. Assume there is always data to send. Okay, and W is window size measured in byte where loss happen. Okay, so W, this is the maximum. Okay, and then I'll have of this one slow start. This is slow start threshold value. So average window size, this is usually 3 over 4 the W, and average the throughput case 3 over 4 W per round trip time. Okay, so average throughput TCP throughput is 3 over 4 times W over RTT. Okay, so RTT is the maximum CW and right. So this is the average TCP throughput. TCP over long path pipes. So example, the segment size 1.5 kbytes and 100 millisecond round trip time, and want 10 gigabps throughput. Okay, so requires W, this is 83,333 implant segments. Okay, delivered. Throughput in terms of segment loss probability L. Okay, so in that case we can calculate the TCP throughput is according to this. Okay, 1.22 times the maximum segment size over RTT square root to R. Okay, to achieve 10 giga bps throughput we required, right? The loss rate is L is equal to 2 times 10 raised to the power minus 10. Very small loss rate. Okay, the versions of TCP for long high speed scenarios. Okay, so that's all. If you have a question or comment, please let us know. Thank you for your attention.